part two of the graphs of special polar equations. So in this part, we're going to look at three different examples. And in the last one, I kind of went through point by point how to graph those three graphs. We talked about the spiral of Archimedes, circles, and one other one. Oh, rose curve is what we talked about. Here we're going to look at three other graphs, and some of them are kind of similar to the three we talked about before. But this time, in an effort to save some time, I'm not going to be going through point by point. We're just going to look at them using Desmos and how these graphs behave, and then we'll kind of generalize at the end. So let's run over to Desmos and take a look at them. I've got them all set up here, ready to go. And we'll start with the first one. It's r equals 3 plus 3 cosine theta. And so I'm going to turn that one on, and we get this looking graph. It looks kind of like a heart. My children say it looks like something else, but I'll let you think about what they were saying. Anyway, so this one is called a cardioid, and we'll write that down in just a minute here. But this behaves like this. So if you have 3 plus 3 cosine theta, let me change this to a sine and see what happens instead of cosine. So if it's sine, then that just is going along the y-axis. If it's cosine, it goes along the x-axis in terms of like where the heart part is. What if I made this negative instead of plus in the middle? What's going to happen there? Looks like it's to the left instead of to the right. So these graphs, we'll run back over to a presentation here. These are called cardioids, and they're in this form: r equals a plus a cosine theta, or r equals a plus a sine of theta. And they're going to look kind of like these heart shapes. We'll come back. Well, let's go back to the Desmos and see what about the distances here. I see from like 0 to 6 we go. And then what about the other stuff? So let's take a peek at that one more time. So I'll go back to plus. Let's change this to, instead of 3, let's change it to 4 and 4. So if it's 4 and 4, it looks like we go from 0 as where that heart point goes out to 8. And so the 4 plus 4 gives us 8. So from the center to the outside is going to be a grand total of 8. Okay, so we'll get into that a little bit more, but let's look at the next graph. And it's 2 plus 4 cosine theta. And that one looks pretty darn similar, except it's got this little curl in the middle. And so this has a different name. But what's different about this equation is the 2 and the 4 are different, whereas in the cardioid one, the 4 and the 4 were the same. So if you take 2 plus 4, that's the distance from the center, or where that swirl happens, out to the outside. That would be 6. And if we think about this, the biggest that cosine can ever be is 1. And then if you multiply by 4, the biggest that will be is 4. And if you add 2, it's going to be 6. So that's why it's going to be 6 out here. And then the smallest cosine can be is going to be 0. And then 4 times 0 is 0. Excuse me, the smallest it can be is -1. So then we get -4 plus 2 would be -2. And so what's happening is when we're graphing this at 180, we're actually going back 2. So it's technically a -2. That's where that inside swirl happens. And when you graph these point by point, you'll see that you're doing some negative points in there. And we'll look at that in the graphing calculator in just a minute as well. So if I change this to like a 5, then now our little swirl gets a little bit bigger. We go out to 7. If I change, let's switch these around. So let's make this 5. There's another cardioid. But let's make this 2. Well, now we don't get a little swirl in here, but instead it's kind of like a misshapen circle. So this, and maybe we'll go a little bit less pronounced. If I make this 5 and 4, we still get kind of like that little point in here, but we're not getting any swirl in the middle. So what we kind of noticed is if the number, the coefficient out in front of cosine is smaller, we don't get the swirl. If it's bigger, we get the swirl. And if we change this to sine, we get the same idea, just as going along the y-axis. So that's been kind of a trend with all of these graphs. And I'll switch this back to 2. There's our original one just with sine, so it's going up and down. All right, so back to this. This thing is called a Limacon. This is that little French letter, the C with the little 3 underneath it. I'm sorry, I don't know what that's called. Anyway, Limacon is in the form a plus b cosine theta or a plus b sine theta, and you get graphs that look something like this. So it's kind of a cardioid is a specific type of limacon, and a cardioid is where it has a point that reaches right at the center here, whereas a limacon sometimes has a swirl and sometimes goes out, and then the point is not at the center. Okay, so limacon is the name of that one. Our next one is, well, let's go back to the presentation so you can see where I got those. This is r squared equals 9 sine 2 theta. And so in order to graph this, I can't graph r squared equals. So what I needed to do was I needed to square root both sides. And so when I did that, I got r equals square root of 9 plus sine 2 theta, and r equals negative square root of 9 sine 2 theta. So I'm going to turn these on. There's the positive square root, and there's the negative square root, and they happen to be right on top of one another. So when you square root both sides, the plus or minus doesn't really matter that much in this example because they are right on top of each other. And we get this kind of cool looking infinity symbol. If we change this to, I'm going to turn one of them off. If we change this to cosine, then it's right along the x-axis. For sine, it's kind of diagonal. If I change this 9 to a 16, it does that, but if I change it to an 8, well, no, that'll work. 16 looks like that. 9 looks like that. So this is really similar to a rose curve that we talked about in the first example. But the difference here is we're doing the square root of both sides. And so we end up with this type of graph. And so this one's called, let's go back to the presentation. Suspenseful. All right, this one's called a Lemniscate. And so they're in the form r squared equals a squared cosine 2 theta, or r squared equals a squared sine 2 theta. And they're always going to look kind of like this infinity symbol, kind of a rose petal or a rose curve with only 2 petals. So if you're graphing these, if you're asked to do the task of graphing any of these, and you have a graphing calculator, it might be a nice tool to use. A couple pointers on this. I have this Lemniscate already typed in. And if I'm going to set up my table, I want to go second window, and I want to have my table start at 0. And with Lemniscates, I want them to go up by 15. And the reason I want to go up by 15 is because at 2 theta, that means we're doubling the theta. So that means that with 15 degrees, we double that and we get 30. So we're doing like the sine of 30. And then with 30 degrees, we're doubling it. We're doing the sine of 60. And so that's why I want it to go up by 15s each time. And then to get the table so I can graph it on my polar graph paper, I hit second table. And it gives me the points. But I want to show you something here. As we go down, we get a bunch of errors. And why do you think that's happening? So why are we getting a bunch of errors here? And you should think about, remember, we're square rooting. So what is r squared in these examples? So if we go back to this equation, in this equation on the right, the 9 sine 2 theta, you guessed it, is going to be negative. So when we square root, we get non-real answers. And so when your calculator gets that, it shoots out an error message. So there's no points graphed along anywhere between 90 and then 180, it picks back up again. So there's nothing graphed here, and then you get a bunch of points between 180 and 270. And so this is why it's a little different than the rose curve, because we're square rooting and we're eliminating some of those petals, I guess. And then with the other ones, if we want to graph them, I can go like 4, plus 4 cosine theta. And then what I would do for the table set for those is I would start that at 0. And then we could go up by 30 degrees instead of 15 degrees. You don't need that many points. You could go up by 15. It's fine. It's just going to take you a little bit longer. But we're not doing that 2 theta in our equation. So we hit second table, and then we get all of our points to graph that way. All right, so that was part 2 of graphing special polar equations.